Woohoo, all right. Brief review. Yeah, this is supposed to be stuff we've already talked about here. Previously in a calculus class, perhaps you've done these before. Hopefully you've done these before. Yeah, we talked about derivatives and their meaning and so forth and so on. Start you off with an easy one, right? Right? F of x is x squared minus 2x plus 8, and so the derivative is what? What's the derivative of that? 2x minus 2, right? Just some power rule. The plus c? Yeah, the integral is where you utilize plus c. On derivatives, yeah, you don't do the plus c. The integral is the antiderivative, and that's where you have the plus c. So yeah, that's a good question. What does the derivative represent? Question 1b. Well, it represents a couple of things. If we're talking graphically speaking, what is it? Slope of the tangent line, isn't it? Yeah. Graphically, it's the slope of the tangent line. Now, we also looked at the application of it to, like for example, if it represents, say this function represents a position function, how high something is, or if it represents a volume, say that, what are we talking about derivative there? Rate of change, yes. Application-wise, it's the rate of change. Derivative is either the slope of the tangent line or it's the rate of change. In this case, it would be the rate of change of f with respect to x, right? It's how fast the function is changing with respect to x. Okay, so anyway, quick review of that. Now, along the way, we did talk about some rules. Because on number 2, yeah, I can certainly do the derivative of x cubed, and I can do the derivative of cosine of x, right? Remember your trig function derivatives. We'll talk about those along the way. But no, to do this derivative, I don't just do the derivative of x cubed times the derivative of cosine, because why? I have to use the product rule. Yes, product rule. And you remember it's first times the derivative, or this is the way I do it, first times the derivative of the second plus the second times the derivative of the first. Or you can do it in some order. I think some of you may have done it in a little different order, but that's what you got to do. You got to alternate which one, right, you do the derivative of. So I would do x cubed times the derivative of cosine, which the derivative of cosine is negative sine. And then I do the cosine plus the cosine then times the derivative of x cubed, which is 3x squared. Power rule. Remember, bring down the power and subtract 1. We did really rehash that, but all told then we've got what? Minus x cubed sine of x, probably the way we'd write it, plus 3x squared cosine of x. Is that what you all got? Now you do, right? Okay. Well, what about number 3? That's our old friend quotient rule. And the way I like to remember that, or it helps me anyway, low d high minus high d low over low squared. Low d high minus high d low over low squared. Is my little abbreviation for that. Okay, so y prime here would be low 3x plus 2 times the derivative of the high, which would just be 2, minus high 2x plus 1 times d of the low, derivative of the low would be just 3 over low squared. Y'all see that okay? Do I need to dim the lights or anything? I think it's pretty good. Okay, so that would, hey, this can work out nice because that's 6x plus 4 minus, that would be 6x minus 3. Distribute the minus and all that. And so, yeah, this one comes out really nicely. It's what, 1 over 3x plus 2 squared? Sound okay? 1 over 3x plus 2 squared. Not my neatest writing, but hopefully you got it. All right. Now, a couple of points on number 4. First of all, the notation's a little different, but remember the d dx stuff. That just means on number 4, I want to do the derivative with respect to x of what's in the parentheses there. And the derivative of what's in the parentheses there, what rule is that? Do I just do the derivatives? Well, there's a little bit of something there, isn't it? It's chain rule. What's the chain rule? Chain rule is when you have inside and outside stuff. I've got tangent on the outside, x squared plus 2x minus 3 on the inside. So what do I have to do there? Well, I have to do the derivative of the outside, which the derivative of tangent is secant squared. And what happens to the inside when I do that? Not a thing. It stays the same. Then I multiply by the derivative of the inside, which is 2x plus 2. Okay, so yeah, that was our 3 main rules for derivatives. Product rule, quotient rule, chain rule, I guess 4 if you count the power rule in there. But we also had that on number 5. Is that okay on number 4? Any question or concern on number 4? I don't think there's any simplifying there, so I'm just going to leave it like that. Okay? Number 5. Well, we ran into these sometimes where we had to do this. I am wanting to find the derivative, dy dx, the derivative of y with respect to x, but how shall I do this for this one? What's this called? What am I going to have to utilize here? Remember? You got to use product rule. What type of differentiation is it, though? Implicit, yeah. The implicit, we called it. Implicit differentiation. And he's right. So, yeah, we have to use the product rule here because on the implicit differentiation, I'm going to basically d dx both sides, take the derivative with respect to x of both sides. But to do the d dx of the left side there, I'm going to have to split it up into a product, aren't I? 2x times y squared. So it's a product rule. So the first times the derivative of y squared. Now the thing is, when I do the derivative of y squared with respect to x, yeah, it's 2y, but since I'm doing the derivative with respect to x and it's a y thing, remember I've got to put in the dy dx. Then I'd go the y squared times the derivative of 2x. Well, that's just 2 because I am doing just a thing with respect to x. With me on that? So all that is the derivative of the first. Now the second part also have a product, so I have to do x squared times the d dx of y. What about that? Well, the derivative of y is just 1, but it's a y, so I've got to do dy dx with it, don't I? Then I would do the y times the derivative of x squared, which is just 2x. When I'm doing the derivative of x with respect to x, I don't need the d dx stuff. Now what about the derivative of the left side? It's a constant, so it's 0. So I have 4xy dy dx plus 2y squared plus x squared dy dx plus 2xy equals 0. Now what? Yeah, move the non-dy dx's to the other side, and then I can factor off the dy dx on the left side. So I have dy dx times 4xy plus x squared equals, and those will be over there, so it'll be a minus 2y squared minus 2xy. And so then all I have to do is divide off the 4xy plus x squared. Right? Remember all that? Vaguely? Sort of? Kind of? If you say so. Okay. All right. Number 6. What is the definition of the derivative of a function f? Yeah, from time to time, we will bring out the old definition of derivative, just to help us see what derivative something new might have. And so we'll need to recall the definition of derivative. And the definition of derivative I'm referring to, of course, the limit definition. F prime equals the limit, and we did it a couple ways, but if we go the limit as h approaches 0, it's what? F of x plus h minus f of x over h. And then to do it that way, then you simplify f of x plus h, subtract f of x, divide by h. Hopefully, you have to use some things like the conjugate sometimes, factoring sometimes, combining fractions. So lots of good stuff can happen if you do it that way. But just want to remind you that. We don't have to do that a whole lot, but in case we do, remember that. And again, remember that's the secant lines. That's doing the limit of the slopes of the secant lines and all that good stuff. So all that's from way back in our past, right? Somewhere in the depths of our minds. Okay, integrals. A couple of those real quick. Evaluate the integral. Well, of course, the first thing is on the integral, we really want to get it where we can do the antiderivative, do the opposite sort of thing. So when I go the antiderivative of x squared, what do I do? Add 1 to the power, and then divide by that power, so it would be 1/3 here. And then the same thing, I'd go minus 2, so I'd have x squared, so I'd divide by 2, so that's going to be 1. And then what about the minus 8? Well, you have to add the x there. And now in this case, we don't have to add the c because I'm doing the definite integral. I'm just going from -3 to 0. So yeah, that's 1. So plug in the 0. Hey, that's good. That's just all 0, isn't it? Then I'd do the minus of the -3, so it'd be 1/3 minus 3 cubed minus -3 squared minus 8 times -3. All that, of course, that's 0. That's going to be -27. So that's going to be. Come back, please. There you go. I don't think I need this too much longer. All right. So that's going to be what? -9. And then minus -9, so, or minus 9 again, plus 24. So I'm getting minus 18 plus 20, minus 6. Or something along those lines. Okay, now, what does that represent? Graphically speaking. Well, if I graph that x squared minus 2x minus 8 graph, here's what it looks like. something like that, right? Is that what y'all get? Where this is negative 3 right about here. Well, what does this represent? Area under the curve. We say area under the curve, but technically speaking, it's what? It's this area under this here, and then this here, but this here, of course, is a negative value, and then all told, it comes out to be net a negative area. So it's the net area between the curve and the x-axis. That's what it is. And in this case, it looks like the area below the x-axis outdoes the area on the top of the x-axis. So just remember that. There's other different things, but okay. Now, 8a and b, a couple of important ones there. What about that 8a? Probably I'd want to rewrite that, right? And say this is the integral ax, not a over x squared, but ax to the negative 2 power, yeah. Make it a power on the top there. And then what about the square root? Yeah, make it a 1/2 power there. And I threw in the a one because what about a? Yeah, just treat a as a constant, like a 3 or a 50 or whatever, and just do your power rule there. Now, when I do the power rule, x to the negative 2, I'm adding 1. So it's going to be a, and it's going to be x to the minus 1, minus 2 plus 1, so that is minus 1. So I'm going to divide by minus 1. And then the 1/2 power, I'd add 1 there, I'd get 3/2. And when I do a 3/2 power, what happens to the number in front? It's a reciprocal of 3/2, be 2/3. And then this one is an indefinite integral, so that's where I add plus c. So I wind up with minus a, x to the negative 1, or however you want to write that, plus 2/3, x to the 3/2, plus c. How about that? Okay? Now 8b is another important one, because what shall I use here? Anybody get that one? U-substitution. Let's use U-substitution. U equals what do I want you to be? X squared. Yeah, the problem is on integrals, I don't have a product rule for integrals, antiderivatives. So I have to do various other things, and one of the various other things I can do is the U-substitution, and I'm going to let U be that inside stuff there. And so then I get du to go with that, which would be 2x dx. It's our differential. It's the derivative times dx. And then the way I did it is go ahead and solve for dx there, because I'm going to substitute for dx. Du over 2x is dx. So make that substitution, so I have the integral of 6x times the sine of u, and then dx is du over 2x. Make my substitutions there. And then if all works nicely, this x does cancel out with that x. Of course, the 2 cancels and gets me 3. So I have 3. I have the integral now of 3 sine of u du, which is now just a straightforward antiderivative, isn't it? I can do the antiderivative of sine, so it's 3 times the antiderivative of sine, which is negative cosine. Yeah, it works the opposite on antiderivatives. And then plus a c. And then the very last thing is to go back to x, so it's negative 3 cosine of u was x squared, so it'll be cosine of x squared. So yeah, don't forget about U substitution for integrals.